This is the first mini lecture for section 7.3 and section 7.4, which I'm going to cover together. We're going to continue our discussion of the real numbers by talking about ratios, proportions, and percents. When we talk about a ratio, we are talking about the relationship between two parts, or a part to a whole. We're only interested in how they relate to each other, not their absolute sizes. Think about squares, for example. The ratio of the diagonal to the side of it is the same, no matter the size of the square. So I could have a small square Think about the relationship between its diagonal and its side. Or I could have a large square. Same shape, but larger. And think about the relationship of its diagonal and side. So it's the same relationship in each case. The diagonal is a certain number of times the length of the side. That number of times is the same, whether it's a small square or a large square. Okay, and the ratio here happens to be the square root of 2. So if if A is the diagonal and B is the side, then in each case that ratio, which I could write as A over B, or as A to B, kind of the more old-fashioned form like that, that ratio is, or could be interpreted as, the real number, the square root of 2. Okay, so one way of thinking about a ratio is that it's like a fraction, but with real numbers instead of just integers. So let A and B be real numbers, with B not equal to 0. Then the ratio of A to B, also written ratio of A to B with a colon, that's kind of more old-fashioned notation. That's just the quotient, A divided by B. That's one way of thinking about it. But normally when you're talking about a ratio, you're not just talking about the real number quotient. You're really thinking about these two parts and the relationship between them. Okay, so for example, like we just saw, the ratio of the diagonal of a square to its side is the square root of 2. If I take the diagonal, divide it by the side, I will always get the square root of 2. Doesn't depend on how big the square is. Here's another example. If a car uses 16.7 gallons to go 394 miles, then its average rate of fuel consumption is this ratio, 394 gallons to 16.7 miles. And if we compute that ratio, we get about 23.6 miles per gallon. So that's an example of a ratio. Okay, and if we took the same car and we only drove half as far, then we would only use half the number of gallons, but we'd still get the same miles per gallon, presumably. Okay, two ratios are said to be in a proportion if they represent the same relationship. If A over B and C over D are two ratios and their quotients are equal, then this equality is called a proportion. There's kind of a little bit more of an old-fashioned way of thinking about this, which is like an analogy, and I think it's a very good way to think about it. So when I write something like this, it's like an analogy. A is to B as C is to D. Okay, you learned non-mathematical analogies in school at some point probably. They usually form part of the SAT. So for example, kitten is to cat as, what? I guess puppy is to dog. Okay, the same analogy could be written in different ways. So you could also say puppy is to kitten as dog is to cat. There's different equivalent ways of writing the same analogy. And the same is true of proportions. So I could rewrite this proportion up here as C over A equals D over B. Also true. Okay, but of course there are some ways that are not equivalent. So I would not be able to say something like kitten is to cat as dog is to puppy. Right? That messes the order up. Same thing goes for proportions. I can't just do anything with those four numbers. Okay, some things are equivalent, but some are certainly not. Okay, so for these analogies involving ideas, you have to use language and intuition to be able to fill in the blank. With numerical analogies or proportions, we have a rule that we can apply, which is just cross multiplication. So A over B is equal to C over D if and only if A times D is equal to B times C. For example, a diorama represents a house that is 30 feet high using a model that is 9 inches tall. So the house in real life is 30 feet high. In the model, it's 9 inches. How tall should the model of a car be if the real car is 5 feet high? So I could say something like this. Well, we've got 30 feet. I'm going to write it first as an analogy. 30 feet is to 9 inches as 5 feet is to, blank. Yeah, there's other ways of writing it, though. So in this way I wrote it, on one side we've got the house. On the other side we've got the car. Okay, here's another way of writing it. I could do feet and inches. So I could say 30 feet is to 5 feet as 9 inches is to, we don't know how many inches. So here, that's the real things. Here, that's the model. But you see there's some consistency where, this first way I write them, on each side we have feet to inches. Feet to inches, feet to inches. Down here, where I've got real versus model, on each side I have house to car, house to car. So as long as it's consistent, then it's fine. It doesn't really matter how you set it up. So if I use this first one, I get this proportion 30 over 9 is 5 over x. Okay, cross multiply. 30x equals 45. So x is 45 over 30, which comes out to 1.5. So the car should be 1.5 inches high. So, just knowing how one real object compares to the model tells you how everything else relates. Okay, and that is a relationship that is known as proportionality, which we will talk about in the next mini lecture.